that sort of follows along, right? So people have argued for some sort of a chemical a medium for memory that then has to be read out by the nervous system. Like that's one example. We've done and like McConnell found this in the 60s, but we've done this work in planaria where you train them and you chop off the whole head and they regrow a brand new brain from scratch, a brand new centralized brain from scratch, and then they have recall of the original information. So Earl, could I follow up on that? You're talking about storing information. Could you give your view of what you think the basis of memory storage is in the, classically in the brain? And then I'm going to ask you for how that might fit with some of the sort of weird edge cases that we see.
Huh. Well, I think, in terms of, I keep saying the 20th century connectionism models, if in a dismissive way. I don't mean to be dismissive. A lot of the brain does work like that, and that was certainly foundational. You don't get to where we are now without going through building up the system, first cataloging it, and figuring out the basic units of it. But I think in terms of memory storage, that's where the connectionism model is largely correct. The brain stores information via synaptic plasticity, changing the weights of connections to neurons, and the information gets baked into the brain that way. What I'm saying is that when actual thought comes along, that's not storing information, that's expressing information, that's expressing thoughts. And when that happens, that's where these electric fields and these emergent dynamics really begin to play a major role, because that's how a lot of the computation takes place.
And do you think that does that so the standard view of the synaptic plasticity and all that, does that require for these structures to hang around? People have memories that are 80 years old and things like this. How much of an issue is the constant sort of turnover of all of this stuff?
Well, as long as the turnover maintains the existing patterns of connections, you could just replicate the whole brain, have a completely different brain, next week, and it'll also operate the same. So that's a challenge. You got your whole body's, constantly regenerating itself for the most part. But you just got to maintain the pattern of connectivity. But you're about to tell me, I suspect, some alternative view of memory that can accommodate this massive turnover. So go ahead.
Well, I'm not going to try to float a different view of memory, although I have some doubts about the standard story. But there are a few cases that I think are interesting in that respect. First of all, for example, the scenarios of memory transfer. So memory transplant. So in a variety of systems, and some of it was done for simple memories. It was even done in rats, but most of it is in sort of the so-called lower life forms. You get these experiments where either cells or oftentimes extracts. So either brain extracts, or in some cases not even brain extracts, are moved from a trained donor to a recipient, and there's some degree of recall that sort of follows along, right? So people have argued for some sort of a chemical a medium for memory that then has to be read out by the nervous system. Like that's one example. We've done and like McConnell found this in the 60s, but we've done this work in planaria where you train them and you chop off the whole head and they regrow a brand new brain from scratch, a brand new centralized brain from scratch, and then they have recall of the original information, so you can see information then moving. We can't say it's non-neuronal, but you can see you have to move on to the new brain. There are those kinds of things,
Yeah, I know. Yeah, and you're right. I mean, the thing to remember is that living organisms had behaviors and can learn and stuff even before we had nervous systems. You can do simple classical Pavlovian conditioning just in single cells with just chemical gradients. You don't need a nervous system to do that. Nervous systems are a way of expanding on that basic repertoire and getting more and more complex behavior. So yeah, so I believe that simple memory, simple behaviors can be transferred in a chemical way. But when I'm talking about memory, I'm talking about higher forms of memory, like recall and a personal recall and stuff like that, and our knowledge baked in. I think that's got to be somehow involved in the patterns of connections between the neurons, because we know that they change as a result of learning. And so what I'm saying is that's a great way to store things, but not a great way to do computation. But yeah, I mean, their memory and learning predates nervous systems. So some of the stuff on chemical transfer from one trained animal to another doesn't surprise me that much, although it's a beautiful, elegant work.
And what do you think about we just did a review of clinical cases where you've got humans with normal, in some cases above normal, intelligence performance level, and radically reduced brain function. There are some crazy cases where somebody's shown finally an MRI or
Half their brain's missing. Yeah, yeah.
like, or much more. Right, there are these very hydrocephaly cases and so on. Like, what do you think is going on there?
Well, I think brains are very, very plastic, and especially if the disruption happens very early in development, brains can develop around that and accommodate a lot. If you see that kind of damage or change in an adult brain, you're not going to get normal function. No way. The cases you're talking about tend to happen when the change happens very early in development, and brains can sort of develop around it. But you're not going to see that kind of thing in the adult brain.
Yeah, I'm with you that the plasticity must be important in some way. But what I find curious about that is that my understanding is that we are under considerable selection not to have very large heads because of the birth canal and all these things, right? So there's some pressure on not having a giant brain. So it seems to me that if there was a way to get the same level of performance out of far reduced. That's what's weird to me is that some of these cases you get very normal performance out of a much reduced amount of brain mass, and it would seem to me that evolution would be under, and not to mention the energetics of the brain, right, and how much of our energy budget it's chewing up. Like, it seems like if there was a way to get all of that with a much smaller brain, it seems like there's a lot of pressure to do that. It's just
sure, but Mike, I think every time this happens, you don't end up with a person who grows up to be a normal adult. A lot of times it happens, the person ends up with severe learning disabilities or dead. So you're hearing about the few successes, not about the average case. First of all, and second of all, the thing about the plasticity of turnover, one thing that I always try to remind myself is there's something in the brain called multiple realization. So, for example, I think it was Eve Marder at Brandeis. She studied lobster pyloric motion. That's in the lobster gut, and that's just moving food down in the intestine. Simple action, and that's so just like squeezing a tube, and that's explained. Three ganglions of the neuron in the lobster gut are responsible for this. And I think Eve found that you can. I maybe get the exact numbers wrong here, but you found that there's computation. There's 100,000 different ways you could tune up these three ganglion and get the exact same pyloric motion. So there's lots of ways in the details to do the same things in our brains. Even with the turn over, you form a memory in this synapse, for example, then it turns over. Well, there's lots of other synapses and lots of redundancy, but the exact details don't matter so much as the principles that arise out of it. So you could have 100,000 lobsters, all with their ganglion tuned up 100,000 different ways to get the exact same function. And in a lot of ways, that's where our brains are. I mean, like you're born with your cortex, you're born with way too more connections than you're going to have. What happens when you're a young infant is the connections get winnowed away, and you're left behind with connections that represent reflect the statistical regularities of the world, like corners and edges and stuff like that. So you're born with a random seed of way too many connections, and your own individual experiences will winnow those down to a fewer number of connections. That's some meaning of the structure of the world. Well, that means all of us are born with slightly different brains, different brains in the details, and we all have different experiences. So all our brains are wired up in the details in a different way, but they all operate on the same principles. And if you think about it in terms of less about exact anatomy, then the principles that arise out of the way the anatomy interacts with these emergent properties, then the details and the turnover and things like adaptability seem like less of a problem.
Earl, do you think there's evidence that humans can store memories outside of the brain? I was speaking to Nikolai Kukushkin from NYU. He seems very convinced that, we can argue that maybe cells by themselves have memories related to their own specific goals, but I'm talking about actual human memories here, the memories that we have as a human unified system. Is there any evidence that those memories can exist outside of the brain?
Memory is a broad term. Do you mean what I did yesterday, what I watched on TV last night? Or you're talking about some sort of more broad kind of for memory, because certainly we're learning a lot more about interactions in the brain and body. The brain is not isolated from the body. It's constantly getting metabolic and other information from the body and then feeding back and changing things. So it's an interacting system, and little things like metabolism make a huge difference in the brain function. So it doesn't surprise me that there's going to be memory in the system. The brain is the system together with the body. There's going to be memory in that system, but I'm trying to understand how specific or high level of memory are we talking about.
What about an actual autobiographical memory, like an actual memory of your life?
I don't know of any evidence, and Mike, or you can correct me, where there were actual autobiographical episodic memories, we call them, where they're taking place somehow outside the brain. Is there a study that shows that? I don't know.
I mean, so I'll tell you the kind of study that could. I'm not sure the evidence is very good yet. I think the cases are few, and there needs, and I'm not aware of an animal model, unfortunately, for it. So we have to kind of wait till these clinical cases show up. But the kind of case that I've seen case reports of memory transfer, or I don't know if you call it memory, but transfer in heart-lung transplant patients. So one of the things that you occasionally see in cases of heart-lung transfer is not specific episodic memories, but personality traits. So there have been claims of specific personality traits moving over from a donor. Now, this is obviously like a wild claim, right? So I'm not saying the evidence is strong at this point, but if that were to be true, I think that would be the kind of thing you're talking about. And then, sure. and I'll tell you an experiment that we're doing now that's kind of fun along those lines.
Just interrupt just 1 second, but we keep talking about case studies. Remember, case studies they're not study. They're other descriptions of one-off. So case studies are examples. Here's something interesting we should investigate. They're not strong evidence in and of themselves.
Yeah, 100%. Yeah, I think if the case studies pile up, then I think it suggests that we need a model system to really study this.
Sure.
So the closest thing that I can think of, and so we're gonna do this shortly. I don't know if you've heard of these anthrobots. So we take adult human patients, donate tracheal epithelial biopsies when they go in for sampling, and we take the cells and we allow them in the culture conditions. What they do is they reassemble into a little proto-organism that basically moves around on its own because it has cilia. So they run around on their own. They have all kinds of cool properties. They express 9,000 genes differently than they otherwise would. They can heal neural scratches and all kinds of stuff. But one of the things we're interested in doing is, when you buy these things, you get a little sheet on the patient that donated them. And what I want to do, and some of them were smokers. So what I'd like to do is to get so you see where this is going. I'd like to make anthrobots from smokers. I'd like to see if the anthrobots show an affinity to nicotine. They don't have a nervous system. They're entirely work out absolutely may not, regardless. It's amazing, but that's the kind of experiment I like to do, right? That if it does work out, then we're overlooking something. So
sure, but a chemical sensitivity isn't the same as an episodic memory, though.
No doubt, no doubt. Yeah. That would be a very simple, low level kind of thing. But still, what I think. But if it does work, what I think would be cool about that idea is that you typically, so what you started with is a patient in which some kind of cells, presumably in the brain, are addicted to nicotine, and then they drive muscle-based behaviors to go seek out nicotine. Right? In a rat, presumably that's the story you would tell, that there are neurons that are addicted to nicotine, and then you have this like muscle-driven behavior to go get the nicotine. In the anthrobot, there are no muscles, there are no nerves. So you're remapping whatever is going on there, you're remapping it onto a new architecture where you now have epithelial cells and you have little cilia, which is how you row, which I think is cool. And biology tells us that works because of the caterpillar butterfly memory transfer. So there are experiments, right, where again, trained caterpillars pass on their memories to the butterfly, which never mind how the information survives the tear down to the brain. To me, the more interesting thing is that you've now remapped it on a completely different sensor and effector array. So you no longer move like a soft-bodied creature like a butterfly. You move now in 3 dimensions. You fly with a hard body kind of architecture. You don't care about the leaves that you chewed as a caterpillar. Now you want the nectar, and like all these things are different, but but the memories get remapped. And so I would love it if I think it would be fascinating if we could show in a mammalian system that those kinds of addiction to the nicotine would then remap onto a different body plan, which is what the anthrobots do. And then what I'm going to do, if that does work, what I'm going to do is take the anthrobots, I'm going to stick those into a rat, and I'm going to see if we can then pull it out, pull the inflammation back out, and have the rat now back to the muscle based motion. Right. So this is
see if the rat will pop down to 7-Eleven for a pack of smokes.
The Giant Shoulder mission is to explore radical ideas in biology, neuroscience, and consciousness, and elevate those stories to the highest possible level while keeping them accessible to everyone. If this interests you and you want to support independent science, then please consider subscribing to the Clips channel